Hi, Year 10. So today we're going to do a little bit more about velocity time graphs. We did a little bit at this yesterday, and today we're going to explore the world of graphs and all of its fascinating aspects a little bit more deeper. So we're going to be looking at how to measure changes in velocity using a graph, explaining the different parts of the graph and interpreting what the graph is actually showing us about acceleration and deceleration. Also, for those of you doing the higher tier, explaining what the area under the graph actually tells us and why that is important. Okay, so back to the rag sheet now. I apologise, I couldn't attach that to yesterday's lesson because it was a spelling test and there isn't a function to add web links at the bottom. However, I appreciate that some of you might still be missing this, so here it is, and I will attach it to today's lesson. So a quick quiz 1 to 11 today, some extra bonus questions. You are going to need a calculator for parts of this lesson, so if you haven't got one now, when you pause the slide, go away and get one and have a crack at these questions for me. So there's the answers. I'm not going to talk through them because you're able to read, so please feel free to mark yourself out of 11. So recap from yesterday's lesson, there are some key words and units that we need to make sure that we're absolutely 100% familiar with. Speed, meters per second, acceleration and deceleration, both are measured in meters second squared, whereas velocity is meters per second. Again, making sure that you can differentiate between speed and velocity is essential. The equation that we're expected to know and be able to rearrange is speed equals distance travelled divided by time. And the key element here for the gradient is that the gradient of the line is equal to the speed or the velocity in a distance time graph. However, in a velocity time graph, the gradient is equal to acceleration. So a little bit more, okay. So acceleration is referring to that change in velocity over time, and we're measuring it in meters per second. Velocity, again, speed in a given direction. That's why it's a vector quantity. I always remember with a bit of alliteration that V for velocity is a V for vector. Okay, speed is a scalar. Okay, and the gradient of the line on the velocity time graph represents acceleration as per the last slide. Acceleration is the change in velocity meters per second divided by time in seconds. Acceleration may be given as a negative as the object may be slowing down. Negative acceleration is deceleration. So just a little bit of maths about the units here, and sometimes you can work out from equations how we derive those units, and it can help us in exams to work out what units we should be adding. Okay, so here we've got velocity in meters per second, and we've also got the change in, being divided by time in seconds. That means we've got meters per second and seconds. Therefore, we have two lots of seconds, which that's why we get seconds squared. All right. We're going to do a little bit of a mini investigation today. I know you're really excited for this. So what we're going to do is you're going to need a stopwatch, your timer. You can use your phone, a tape measure or a ruler. Now, I don't know where you live. I don't know how much space you've got. However, everybody can do this and you can be as creative as you want. You can be rolling tins of beans. You can be running up and down your garden. You could be, I don't know, maybe do it as a lap of your block. Anything you fancy doing, really. Just take this as an opportunity to get a bit of a break and make sure that you are being safe whilst doing it. So we're going to calculate your acceleration, and we're going to do that by doing it on your own. You could rope in your mum, your dad, your nan, your granddad, your cat, your dog, any other randoms that you've got living with you. I don't know what's going on at your place, but you could even, I don't know, measure it with cars out the window if you're feeling particularly lazy. So what we're going to do for today's method, and we're often asked to describe this method in an exam, is we're going to see how it takes for two objects to move across a set distance. And then we're going to time how long it takes for them to do it at a different speed, which then, preferably a faster speed, you can potentially increase a bit of, gradient if you're rolling things, or give it a bit more of a push, or you could actually physically run a bit faster, you never know. And then what we're going to do is you're going to measure the time for travelling both the distances at the same. Distances don't have to be accurate, just give it a rough, measurement. One decent stride is usually about 1 metre. I have got very short legs, if those of you know me. So if you're quite tall, you may want to sort of say it's about 1.5 metres. So just guess if you haven't got a tape measure, no excuses there. And then what we're going to do is measure the change in velocity from the walk to the jog. Okay, so using the equation, acceleration equals the change in velocity divided by time. So we need to create a results table like the one shown here, and acceleration is initial velocity minus new velocity, and calculate the acceleration. Have a go. Rope your family in. You know that your parents really aren't enjoying working from home, and they really would like to jog around the garden. Let's have a go at this. Okay. So once you've got your results, you're going to then make some calculations and calculate them. Now, if nobody in your house is prepared to play ball and you don't really want to do the practical, don't panic, because we've got lots of practice questions for you to have a crack at. And if you feel that you would like some more practice of these practice questions, I will be doing additional packs that you can email me for if you would like. So some questions about a cyclist. They do like a cyclist in these exam questions. They also like a speed boat and a racing car. I don't know why it has to be those three things, but they do enjoy those. So we've got 3 questions. Pause the slide and answer them for me in your booklets for me. Thank you. So here are the answers, and the first question is explaining what's happening at each point in the graph. Now you'll notice with colour pencil, I have broken the graph up into a series of triangles, and that is so that I can easily calculate the gradient. So the first part, E, is 0 per metres per second squared. F, you can see that I've gone from 10 divided minus 4 divided by 10 divided 4 equals 1 metre per second. G, gradient has gone 10 minus 7, which gives me 3, divided by 16 minus 10, which is 6. That gives me 0.5 metres per second. It's a deceleration. And lastly, H, I've gone 21 minus 7 on the gradient, and divided by 20 minus 16 gives me an acceleration of 3.5 metres per second squared. So let's look at the answers. For some reason they keep popping up in different lessons. Maybe when this is all over, you can all show me how to use PowerPoint properly. So question 2, there was 2 parts to it. The first answer is 15 and the second answer is 7.5. 3, well, you can all read. Just give yourself a mark, and make sure that you are including those units. So breaking here, you can see that my graph here, it can be divided into a triangle and a square, and so therefore we need to apply a bit of trigonometry. So we need to use the area under the line, the red line between 0 and 10 seconds, and also the area under the triangle between 10 and 15. So what we're going to be looking at is velocity is constant, and therefore what we need to work out is that by saying it travels 200 metres, that's because we've travelled 20 metres by 10 seconds. Okay, this is the area for the rectangle under the graph. However, the purple area, which is the triangle at the end, we need to do half the triangle. So what we do is do 10 times 15 and then divide it in half, or the height of the triangle times half times the base of the triangle. Okay, all right, I hope that helps. So we're going to look at matching these labels to what's happening, A, B, C, D, and the velocity time graph. And so A is nice and flat, and there is zero acceleration, and so that is double I, part B. B, the red line on the graph, that's acceleration motion throughout, that's part I, or A. Acceleration motion, then decelerating motion, refers to D on the graph, the yellow line. And lastly, is C, which is deceleration throughout, which is that green line, which you can see is going down. Then, looking at figure 1, identify the line representing the object that travelled the furthest distance, the least distance, and the object travelled further. So again, they're really getting their money's worth out of this graph. You do need to make sure that you understand how it's working, and you need to be able to support your answers with the maths. Pause the slide and have a go at the questions. And here are your answers. Okay. So there is a SAM learning task that is associated with this video. Please can you have a go at that, and then the marks will be submitted automatically. I would like it if you don't get above 50% for you to have a second go at it. There are a number of you that aren't, and therefore I'm a bit concerned. Less than 40% of the year are doing all of the work. Can we keep it up, keep it going with it? I know this is difficult, but you can do this. And I've also added some additional exam questions so that you can practice these at home. Thank you.